All right. Okay. So, good to see you all. Good to see you all. Thank you, Dalton. What was I saying? Oh, so I missed you all last week. Sorry about that. I mean, I guess I really shouldn't apologize. I got COVID like almost everybody else at some point. But I'm feeling 100% now. I started testing negative on Friday, so I am good to go. And excited to get one last time to be in here with you all and talk about some physics. So let's do that. Like I said, I've called this has nothing to do with the content. It just has to do with the fact that it's the last lecture of the quarter. Right? This is it. As I said, you have no scheduled commitments for this class next week. You have no lecture because there's a holiday. You have no DLs because we're out of DLs. There's nothing left. The only thing that we have next week is these review sessions, which we'll be posting that schedule by the end of this week. And you are welcome to attend as many or as few of those review sessions as you want. You are not required to go to any, but you may attend as many as you find helpful. So those are the only things we have left for this class, and I hope you take advantage of those, or you take the time, if you think this would be better for you, to take some time off and relax and prepare mentally for the week, even if you're not actually studying. So whatever you think is best, that's what you should do. But this is basically all we have left. So, like I said, here's the plan for today. Quiz, check, we did that. Finish up thermodynamics, statistical mechanics. That's what I'm going to do next. And then I'm going to do a brief review, right? Again, this is not going to be a comprehensive review. It's just going to be sort of an overview of all the topics that we've seen so that we can use it to help guide studying. And then, again, my little rant, which we'll get to. Okay, so what did we do last time? As usual. We introduced this idea of statistical mechanics, right? And the way that we presented this, we said, okay, let's imagine that we want to make a perfect model of a gas. A perfect model. And by perfect model, we mean a model that can answer any and all questions we could possibly ask about the gas. In practice, this is impossible. In practice, this is impossible, right? So instead, we think about the statistics of the entire system. Now, this is not a stats class. You're not expected to do any of the statistics. But under the hood, a lot of the stuff that we've been learning this quarter is there's actually a lot of statistics sort of going on in the background. We just aren't learning it because it's mathematically really complicated and we don't want to do that. And the idea is that particles in a gas are sort of bouncing around randomly, as far as we're concerned. They're basically bouncing around randomly. And so because of that, we can imagine that there's this probability thing, right? So a microstate is a specific arrangement of each individual particle in the system. Now, we're never going to specify the microstate, right? The microstate would tell you exactly where every single particle is, how fast it's moving, which direction it's going, is it rotating, is it vibrating, all that stuff. That's not something that we're going to do. But what we can think about is the macrostate, which is the larger scale properties of the system, so things like pressure, volume, and temperature. And it turns out that some things are just more probable because there are more microstates that give you that macrostate. And so the classic example I used was the case of a box of particles with all the particles shoved up into a corner. And if you let them go, those particles are going to spread out and sort of take up the entire box. And one way of thinking about why that happens, there's a couple of them, but the way that we're thinking about now is that there are more microstates where the gas is evenly spread throughout the box than there are microstates where the gas is up in a corner. And so because of that, the particles will tend to spread out. Now, there's actually a lot of things in physics that are kind of like this. It's not that they're impossible. So let me step back. It is not impossible for the particles that are bouncing around randomly to randomly show up in the corner of the box, right? That is not impossible. It's just so incredibly unlikely that for any sort of normal amount of particles, if you were to watch a box of these particles for the amount of time that the universe has been in existence, you still probably wouldn't see it. That's how unlikely they are. There's another example. This is tangential, right? But there's actually a lot of things in physics like this. For example, if you ran full tilt at that door, there is a tiny but non-zero chance that you would pass straight through it. And when I say tiny, though, I mean very tiny. So please do not try it. But if you did that over and over again for trillions of years, eventually it would happen. eventually would happen. There's a lot of things like that in physics, where under the hood, they're actually more probabilistic than they are truly laws, if you want to think of them that way. The universe, at a very fundamental level, as far as we can tell, runs on probabilities, not on specific yes-no answers. So this is how we might calculate the probability of a given macro state. And we introduced this idea called the second law of thermodynamics. Now, I haven't introduced what S is yet. I'm going to talk about that in a minute. But what we said was the second law of thermodynamics says that a system, a closed system left to its own devices, will tend towards the macro state that is most probable. It will tend towards the macro state that is most probable. So again, why do the gas particles spread out when then we push them up into a corner? It's because they, the case where they're all spread out is much more probable. It's just much more probable. And mathematically, we represent that like this. Again, I'll talk about what S is in a minute. It's called entropy. You've probably heard of it, but we haven't really given a precise definition in this class yet. We'll do that in a moment. So what does this all have to do with gases is the big question. And the answer is, wait, that's not what this says. This actually just says what was on the previous slide pretty well, but it says it again. But again, the key takeaway, it turns out that some of the laws of physics are really the second law of thermodynamics in disguise. And the example, which we'll see here later today, is why heat moves from a hot object to a cold object. We'll see that in a minute. So then let's ask the big question, what does this all have to do with thermodynamics, right? So we've studied this law of thermodynamics. There's gases, and they have pressures and volumes and temperatures and all these things. And you might ask, well, what does this have to do with this this microstates thing? And the answer is this. The big picture stuff that we can measure about a gas, things like its temperature, its pressure, its volume, put limits, or what we like to call constraints, on the microstates that the gas is allowed to be in. Right? So, for example, it is not possible for the gas in this box to be in a microstate where its volume is bigger than the volume of the box. The box does not allow it. The box puts a constraint. And so there's this connection between these microstate things that we think of and these macrostate things that we can actually measure, like pressure and volume. So where does entropy come in? Well, first off, you could imagine, right, that if you expanded the box, now the particles have more space. They can be in a microstate where they are larger than the box. So what is entropy? I've said that, like, I've sort of hinted at it, right? It has something to do with heading towards more probable microstates and all that stuff, but what is entropy? For this class, how we are going to define entropy is that entropy measures how close the system is to its most likely macrostate. Now, entropy is very, in pop science and in a lot of and even classes perhaps, entropy is often presented as a measure of disorder. Right? We say the more disordered the system is, the higher the entropy is. I don't like that framing for a reason that I'll talk about in a second. It's not exactly wrong. I just think it's a little bit incomplete. Right? But for our purposes, again, entropy measures how close the system is to its most likely macrostate. So why do I dislike this definition in terms of disorder? Well, the reason is that let's think about a system that has the most entropy possible and ask ourselves, what does that system look like? Now, if I said entropy is disorder, you might imagine that the system is like really chaotic and there's things like just going crazy and it doesn't make any sense and all that. But the reality is if you zoom out even a little bit, a system with the most possible entropy is going to be a system where everything is the same everywhere. That is the system with the most likely entropy. Our best guesses at this point of how the universe will end in a time so far in the future that it can't even I can't even comprehend it. And even like I sit around and think about billions of years all the time. The amount of time that we're talking about here is so long that it makes billions of years looks like a half a second or something like that, right? But in that amount of time, the idea is that the universe will reach this state where it is the highest entropy possible. And what does that mean? No matter where you go in the universe, everything will be exactly the same. There won't be stars, there won't be planets, anything. It'll just be like, I don't know, like lukewarm soup or something. I don't know. Something not great, right? Again, you don't have to worry about it. It's so far in the future that, we'll be long gone. But that's what the high entropy system is. So that is why I don't love the idea of entropy being disorder. Again, is it wrong? Not really. But it's kind of not exactly right either, at least as far as I've presented it. And that's how we're going to think about it. Right? That's how we're going to think about it. So how do we actually calculate entropy? I'm going to show you an equation that you're not going to have to use, but I'm going to show it to you anyway. Mathematically, this is how we would calculate entropy. It involves the Boltzmann constant for reasons that are not particularly important, but it involves the Boltzmann constant, and it involves this thing called omega. And omega is just a variable that we use to describe the total number of microstates that are available to a system. Now, it's not anything you will ever have to calculate. So when I got to grad school, one of the classes I took in my first year of grad school was a thermodynamics and statistical mechanics course. And a huge portion of the course, I'd venture to say most of the course, was dedicated to figuring out how to calculate that omega number for different systems. Because it's hard. It's really hard. For gases, it involves like infinite dimensional integrals and like just mind-blowing sort of weird math. So we're not going to do it. I guess it's not the integral is not technically infinite, because it might as well be infinite, right? So we're not going to calculate it. But the important things for us to remember is that because of this definition, again, we don't need to know why mathematically, but because of this definition, there are some interesting things about it. First, if I have two systems, and this system has some amount of entropy, and this system has some other amount of entropy, and I put them together into a single system, the combined system, well, the entropy of the combined system will just be the two added up, which is nice, right? It sort of makes sense, right? And the other thing is that entropy is actually another state function. So just like pressure, just like temperature, just like volume, all of those things, entropy only depends on the state that you're in, not how you got there. Okay? So those are two of the most important things about entropy. There is a case, though, which we can calculate it, but we're never going to calculate the total amount of entropy of a system. We're only ever going to calculate changes in entropy. And there are two ways we can do that. The first is the case where temperature is not changing. So, for example, a phase change. A phase change. In that case, it's the first equation. You find the amount of heat that goes into or out of the system, divide by temperature, you're done. Right? This is about as simple as the equations we have in this course. Now, finding Q, finding the amount of heat, might take a little bit of time. Once you have the amount of heat that goes into the system, you can find the change in entropy just by dividing that number by the temperature. And if temperature is changing, we have this equation, which looks a little bit more complicated. But it's the specific heat of the system times the natural log of the final temperature divided by the initial temperature. Now, what have I said about when to use Celsius or Kelvin? If you're given an equation where you have to actually plug in a complete temperature like this, that's where you would need to use Kelvin. One way that you can remember that is just imagine trying to calculate this number for the solid to liquid phase transition of water, right? When water goes from ice to liquid, which we just saw in the quiz. If you use Celsius, you would be putting a 0 in here, which does not work. You cannot put a 0 in a fraction. Same thing here, right? If you imagine water that starts at 0 degrees Celsius, you'd have to put a 0 here. That doesn't work. So we use Kelvin, right? We use Kelvin. So let's look at something that we've seen like so many times in this class, but look at it from an entropy perspective. Let's think about this. You have something that's warm and something that's cold, and they're going to exchange energy, right? This is something that we've seen a million times in this course. You have a warm thing, a cold thing. Heat's going to go from the warm thing to the cold thing. But let's look at it from an entropy perspective. Now, I'm calling these reservoirs. Why is that? Because in physics, when we say a reservoir, it's just a fancy word for something that has so much energy in it that if you take a little bit out or put a little bit in, its temperature is not going to change. That's what we mean by a reservoir. You don't need to know that word. That's just what we mean. So what I'm saying is, let's just imagine we put these together and just watch them for a very short amount of time. So a small amount of heat goes from here to here, and the temperatures don't change. And let's ask ourselves, what is the change in entropy going to be for this case? So we start with the warm one, right? Energy is leaving, so heat is negative. And you can calculate a change in entropy because the temperature is constant by just taking that amount of heat and dividing by the temperature of the cold reservoir. And then you do the same thing for the warm reservoir. The only difference is the temperature is different and the heat is positive. And now we ask ourselves, which one of these numbers is bigger? Is it the number for the hot reservoir or the number for the cold reservoir? The answer is the number for the cold reservoir. Why? Because the heats are the same, it's just that one is positive and one is negative. But the temperatures are different. And so the reservoir with the higher temperature will have a lower change in entropy, a smaller change in entropy. Right? And so we have a negative number plus a larger positive number. You end up with a positive number. The second law of thermodynamics is saved, right? Well, it didn't need saving, but the second law of thermodynamics is confirmed, at least in this case, right? And again, the second law of thermodynamics is just a fact about the way the universe works. But wait, you might say. There are cases you can imagine where entropy goes down. So for example, I said, well, if heat's entering a system, then its entropy is going up. If heat's leaving the system, the entropy is going down. And you might say, well, but I turned on my AC this week, and the temperature in my room went down, so the entropy in my room is going down. And you'd be right. The entropy in your room is going down. But what is your room not? It is not a closed system. Your room is not a closed system. Your room plus the air conditioner is not a closed system. What is the air conditioner actually doing? It is pulling energy out of the air of your room and dumping it outside. Pulling air out of the... It's doing the opposite thing that your room would do naturally if you didn't turn on the AC, right? And this is the key thing to remember, is that the second law of thermodynamics is only guaranteed for closed systems. Now, if you zoom out far enough, usually, you can find the second law of thermodynamics still holds. So for example, your air conditioner is plugged into an outlet, presumably. It gets that electricity, it gets electricity from the wall. That electricity is coming from somewhere. We like to think that it's all coming from a solar farm or a wind turbine or something like that. Some of it is still coming from fossil fuels, right? But it's coming from somewhere, and creating that energy also creates entropy, right? And so even though if you're just looking at your room, you would say the entropy is going down, which it is. If you zoom out, you would discover that overall, entropy is still going up. Another great example of this is the human body, right? The human body is a low entropy configuration of particles. What do I mean by that? I mean, if you took all the particles that make up a human body and put them in a big bag and shook it for eternity, you would never get a human being out, right? It's never going to happen. So how do we stay at this low entropy configuration? Well, one way of thinking about why our bodies do what they do is it's all about keeping entropy low, right? We are not closed systems. We are taking in energy in the form of food. We are taking in water. We are taking in oxygen. Those are like the three biggest things for our body, right? And we're using that. Again, there are a lot of ways of thinking about what our metabolism is for. This is just one of them. One way of thinking about it is that the whole point of all the stuff that we have in our body is just to keep entropy low as long as possible. Until, then we can't someday, and that's when it all ends, unfortunately. However, we can do it for a while. And when we do, we're actually increasing the entropy around us all the time. I haven't really talked about what entropy is in this context yet, but it's probably not surprising that the food that you put in has a lot less entropy than the waste that comes out. Life is really, really good at creating entropy. This is what we do. And the whole point is to keep our entropy low so that we can go about and do the things that we like to do, right? Some people it's been said by people who maybe don't know as much about this as they should, that life is a violation of the second law of thermodynamics. They say, well, if entropy always goes up, how can life exist? And this is the answer, right? Life is so good at creating entropy. The planet Earth creates way more entropy with life on it than it would if it was just a rock. And so it's not that life is a violation of the second law of thermodynamics, it's that life is a consequence of the second law of thermodynamics, because the universe can tolerate the fact that we have low entropy because we're creating entropy all the time. And so that's good for us. We'll take it. But somewhere, the entropy is always going to be increasing. Now, what's the nice thing about entropy? One of the nice things about entropy is just like we can use pressure and volume, state functions, to get work, you can actually get entropy, or you can actually get heat by thinking about entropy and temperature. So remember, entropy is a state function. Temperature is also a state function. And you can get the heat out just by this equation. Now, again, it comes from an integral that I will never ask you to do, just like I would never ask you to do this integral. I'm just trying to show how they're very similar, right? Work is related to pressure and volume. Heat is related to temperature and what does that mean? It means that on a temperature entropy diagram, you can get heat out the same way that you get work out of a pressure volume diagram, right? You get the area under the line, and you get the heat, right? And if you need confirmation, right, entropy has units of joules per Kelvin. Temperature has units of Kelvin. You multiply joules per Kelvin times Kelvin, you get joules, right, which is an energy. And that is it. That's the end. That is all the material. Entropy is the last big thing. There is one thing that you might see in your DL manual. I can't remember if it's there in the current version, if we finally took it out, called Gibbs free energy. We're not going to worry about it in this course. It's just like another thing that I didn't want to add on. I don't think it's particularly important. So that's it. That's the end of the material. So what I'd like to do now is just take like 10 to 15 minutes to just do a really quick overview of all the material we've seen in this quarter. Now again, this is going to be fast because there's a lot of material. This is not designed to be like a full review session. It is designed to just give you a feel for what you need to prepare for and what you need to study for. So let's start here. This is the one equation of this course. If you forget everything in a year or 2 years or 3 years or 4 years, however long, right? If you forget all of the formalism, all the equations that you learned in this course, all of it, and you only remember this one, I will be happy, right? Because this is the one that really matters. It's the equation that underpins everything that we've studied, that we've talked about in this course. It says that if the energy in your system is changing, that energy must be going from somewhere or coming from somewhere, or going to somewhere or coming from somewhere. That's what this equation says. If the energy in your system is changing, that energy has to be coming from somewhere or going to somewhere, either as work or as heat. Right? Everything else that we do, if you're sitting on the final and you have no idea what to do, I guarantee that the question, what kind of energy is involved here and where is it going or where is it coming from, I guarantee that question will be relevant, right, at some level. So then we moved on to talk about internal energies, right? Thermal energy and bond energy. Thermal energy is energy that something has because of its temperature. When its temperature changes, thermal energy changes. Bond energy is something that a system has because of the phase that it's in, right? Because of the bonds in between particles. When the phase changes, when it goes from like solid to liquid or liquid to gas or something like that, then bond energy changes. Then we talked about these internal energy, or excuse me, the mechanical energies, which have to do with where the object is and how it's moving. There are three main kinds of mechanical energy. Kinetic energy, which depends on the speed of the object. Gravitational potential energy, which depends on the height of the object. And spring potential energy. Now, there aren't a lot of we don't see a ton of springs in our everyday life. But physicists sort of like to say, well, this thing that we discovered in nature sort of looks like a spring, so let's pretend that it is a spring. And the main thing that we used this for was to think about bonds. Right? We said bonds are sort of like springs. So we'll get there in a second. But what else can we do with potential energies? Well, we can think about forces. Right? And then the interesting thing about forces, we didn't learn a lot about forces in this class. If and when you take Physics 7b, you will learn about forces. We didn't talk about them a ton in this class, but a force is just a push or a pull. And it turns out that force always points in the direction of decreasing potential energy. So if you're holding an object in the air and you ask, why does it fall? One way of answering that question is that down is the direction that decreases the potential energy of the object, and so it feels a force in that direction. So then we moved into the particle models. Right? And the whole point of the particle models was, let's try to understand how the behavior of individual particles in a substance gives us thermal energy and bond energy. Right? And the potential energy that we use to describe this is the Lennard-Jones potential energy. And the important thing to remember about the Lennard-Jones potential energy is it is just a potential energy like all the others. Everything we know about energy conservation, everything we know about potential energy still applies to the Lennard-Jones potential energy. But the key thing to remember is that the Lennard-Jones potential energy always involves two particles that are interacting. It always involves two particles that are interacting. We then moved into this particle model of bond energy. And the particle model of bond energy was based on just two questions, which is how many bonds are there and how much energy is in each bond. And for large numbers of particles, the second answer was so if you're talking about a small number of particles, the first answer is the easy one, and the first question is the easy one, the second question is the hard one. When you're talking about large numbers of particles, the first question is the hard one, and the second question is the easy one. And what we said was, for large numbers of particles, we are just going to say that we only care about the bonds that are right next to each other. That's what we're going to say. And is it going to be perfect? No. Is it going to be exactly right? No, but it's going to be good enough. And then we moved into the particle model of thermal energy, and much like the particle model of bond energy, it was based on two questions. How many modes does a particle have? Or how many, this did not move forward. There we go. How many modes are there, and how much energy is in each mode? And the nice thing is that the second question is super easy. It's always the same. It's 1/2 times the Boltzmann constant times the temperature. Sorry. Oh, yeah. And the second question is how much energy is in each mode. Or the first question is how many modes are there. First question is the hard one. First question is the hard one. But we learned how to count it. Right? For solids and liquids, it's easy. For gases, it's a little bit more challenging. But it depends on two things. It depends on how many particles there are and how much modes each particle has. And like I said, we do know how to calculate that. So real quickly, I'll just remind us of how we do this for gases. For gases, each particle brings with it 3 kinetic energy modes. A gas always has 3 translational kinetic energy modes. So that takes care of 3 of those modes. It will have 0, 2, or 3 rotational kinetic energy modes and enough vibrational modes to make up the difference. So this particle has 3 atoms in it, which means there are 9 total modes. 3 of those are going to be translational kinetic energy modes. Well, excuse me, there are 9 kinetic energy modes. 3 of those will be translational kinetic energy modes. 2 of those will be rotational kinetic energy modes. 4 will be vibrational kinetic energy modes. And because there are 4 vibrational kinetic energy modes, there will be 4 vibrational potential energy modes. We use this to think about heat capacity. Now, why would this relate to heat capacity? The reason is that when you have the whole point of a mode is that every mode has the same amount of energy in it. And so if you want to increase the temperature of your substance, you have to add enough energy to every mode. And so the more modes there are, the more energy you need. The more modes there are, the more energy you need. That sounds like what we call heat capacity. That sounds like what we call heat capacity. We have this way of calculating specific heat at constant volume. And there's this weird fact that modes can freeze out at certain temperatures, meaning they become unavailable. And the reason for that is just that, well, it's mysterious. We didn't really talk about it. But the nice thing is you're not expected to know off the top of your head whether a certain mode is frozen, right? That's not a piece of information that you need to know. I will tell you if you need it. Then we moved into thermodynamics, right? For gases, this is the big new equation of thermodynamics. It's the ideal gas law. It relates the pressure and volume to the temperature and the number of modes. And the interesting thing about this equation is that even though we haven't thought about it, it's actually an energy equation. A pressure times a volume is a joule. The ideal gas constant R has units of joules per Kelvin. You multiply that by a temperature in Kelvin, you get joules. So this is an energy equation of a sort. That's not really how we use it. Again, we typically use it because we know like 3 of these things, and we need the 4th. And we said that the core equation of thermodynamics was not really a new equation. Some people call this the first law of thermodynamics. Because we're talking about gases, when we're talking about thermodynamics, you can sort of replace this delta U with a delta E thermal in your brain, and that's fine, because gases only have thermal energy. It's the only type of energy that these gases have. But it's still just conservation of energy. It still just says that the change of energy inside the gas has to be equal to the heat plus the work. Right? In other words, if the energy in the gas is changing, that change must be coming from somewhere and going to somewhere. We introduced this idea of state functions. only dependent on where you are, and process functions, which depend on how you got there. Right? You have two states that are, if you take a process that goes like this, you're going to have different amounts of heats and work than if you take a process that goes like this. We like to put these things on state diagrams, and the big reason we like pressure volume state diagrams is because we can calculate work by calculating an area inside the line. That's the big thing. That's the nice thing. Of course, I also saw a temperature entropy diagram. We also saw the idea of a temperature entropy diagram, at least, just a moment ago. So I'm not going to review it here, but that's another example of a state diagram. In principle, you can draw a state diagram with any pair of state functions. You could do a temperature-pressure diagram if you wanted to. It's not a very interesting diagram, though, so we can't get anything particularly good out of it. And then the last thing is we thought about statistical mechanics, and we thought about the sort of collections of particles in terms of statistics rather than collections of particles in terms of each individual particle, and trying to model it all, that would be too hard. And then now we're running into the stuff that we actually explicitly talked about today. So that is a lot of material. It's a lot of material. And preparing for a final may seem a little bit daunting, which is understandable. I will post, hopefully later today, but if not Wednesday, definitely by the end of the day Wednesday, a bunch of practice finals. So something to note, you probably noticed this with the practice quizzes. I write problems differently than a lot of other professors who've taught this before. But the goal of the practice, and so you're going to run into some things on the practice final where you're going to work on it and you're like, Patrick would never write that. Maybe you can tell by now, maybe you can't, I don't know. But the goal of the practice final is to show you sort of the spread of concepts that can be on there, and hopefully give you some time to actually practice sort of working with all the concepts. There'll be an equation sheet on them, all that good stuff, so that you can sort of get a feel for what taking the final will be like. Some of the questions on those finals were written by me, but not all of them. I like to err more on the side of giving you lots of practice problems because I think that's helpful. So like I said, I will post those hopefully today, but if not, definitely by Wednesday. And solutions will go up at the same time. Okay.